Today, we're going to focus a little bit more on velocity and acceleration. And we talked about these ideas a little bit last semester, but we're going to go a bit more in depth today. And I'm going to go through them just with an example. And so we've got a ladybug that's walking back and forth from her house in a straight line. We've got a function for the position of the ladybug where t is measured in seconds and the S of t is measured in centimeters. And this is how far from the ladybug's house. So I think we've got like a sidewalk in front of the house and the ladybug's walking back and forth. So we want the velocity function. And so we remember if we're given position to get to velocity, we take a derivative. And why does that make sense? So we remember that a derivative is really computed, it's like a slope of a tangent line. So a derivative of position is a change in position over change in time, and that's giving velocity. That would be like average velocity, but since derivatives give us instantaneous things, the derivative of position gives us instantaneous velocity, so the velocity at a particular point in time. So the velocity function is just s prime of t. This is true in general, the derivative of position is velocity. And so we get 3t squared minus 18t plus 24. Okay, if I take the derivative of velocity, then I get acceleration. And I suspect the problem asks us about acceleration at some point in time. Yep, down here, what's the acceleration? So if I take the derivative of velocity, I get to acceleration. So let's do that. So that will be 6t minus 18 is our acceleration. So that's the second derivative of position, or the derivative of velocity gets us to acceleration. So those are two key things to remember. Position, take its derivative, I get to velocity. Take derivative of velocity, I get to acceleration. And now there's lots of things that we can ask once we have our velocity and acceleration functions. So velocity, think of, that's your speed, but it has a sign. So velocity can be negative, and that would mean that you're traveling backwards or traveling in the opposite direction. Your car's speedometer always reads positive values. So even if you're going backwards, it's giving you a positive number. That's speed. Velocity is negative. So if you're driving backwards at 25 miles an hour, your velocity is negative 25 miles an hour. Your speed is just positive 25. So speed is just the absolute value of velocity, just something to keep in the back of your mind. But if we wanted to know something about when's the ladybug at rest, think about if you're driving in your car, when are you at rest? Your speedometer reads 0, your velocity is 0. So a particle is going to be at rest when its velocity is 0. So when the velocity equals 0. We have our velocity function, that's our derivative here. So we want to know when this is equal to 0. I can factor a 3 out. I'll be left with t squared minus, minus 6t plus 8. And then let's see if I can factor this. This looks like this will factor as t minus 4 times t minus 2. And so this will be 0 at 2 and at 4 seconds. Okay, and this could be a very brief pause. So if you think about this, in order to like change directions in a car, if you're driving forward and then you want to go in reverse, you have to pause also briefly before you start going backwards. The same is true of any particle. To change directions, you have to stop really at some point. So the times that she's at rest, or I guess this is a female ladybug, are at 2 and at 4 seconds. Okay, and so now if we want to know when the ladybug is moving forward, that's going to be when the velocity is positive. And the only times that the velocity can change signs are at 2 and at 4, the times that the particles are the ladybug's at rest. So we could do a sign chart for the velocity. We'll assume in this case that time is greater than 0. It's okay to have negative time though. So we'll put 2 and 4. This is really just a sign chart that I'm doing here. And so if I plug 1 into my velocity function, I'm going to get negative from here and negative from here. So this will give me a positive. If I plug a number between 2 and 4 and like 3, I'm going to get something negative, then something positive. That would give me something negative. If I plug in a number bigger than 4, like 5, both pieces will be positive, so my velocity is positive. So the ladybug is moving forward when the velocity is positive, which is going to be from 0 to 2 and 4 to infinity. So 0 to 2 union 4 to infinity. This means that she like moves, she starts walking from her house, and that's actually, we'll start doing this in the next part. So she starts at her house, she moves forward, which we can call to the right, for 2 seconds. And then she turns around and goes back for 2 seconds. We don't know that she walked all the way back to her house. She might have bypassed it, but she goes back. And then she turns around and she just keeps going and she never comes back. So this ladybug is flowing away. She's not coming home. Kind of crazy. So if we want to know how far she traveled in the first 6 seconds, we have to figure out how far she traveled in the first 2 seconds, then how far she traveled from 2 to 4 seconds because she came back home. I'm sorry, my throat's really dry today. And then how far she traveled from 4 to 6 seconds. So we're going to look at 0 to 2, 2 to 4, and 4 to 6. Okay, this is only broken up like this in this particular case because 2 and 4 were the time she stopped. If she had stopped at 3 seconds and that was the only time, then we'd break this up from 0 to 3 and then 3 to 6. So only break this up based on where she has actually stopped. Okay, so to figure out how far she's traveled from 0 to 2 seconds, we're going to plug 2 and 0 into our original position function. And then we're going to do the same thing here. And the same thing here. Okay, and we might have to put absolute values around these because some of these might be negative, but let's go ahead and do these. So if I plug 2 and 0 back into my original expression, what am I going to get out? Okay, S of 2 is 20. S of 0 is 0. So she went 20 units in the first 2 seconds. S of 4 is 16. Minus 20 is -4, but the negative is only because she went backwards. So if we care about distance, we're going to make this positive. We're going to make that +4. And then S of 6 is 36 minus 16 is 20. So she went 20 units, then 4 units, then 20 units. So she traveled 44 units total. And our units here are centimeters. Okay. So we've already answered the acceleration. That's our second derivative. And now we have to answer, where's the ladybug speeding up and slowing down? And this is a question that most students are going to get wrong. So let's think about this from the point of view of a car. What does it mean to be speeding up or slowing down in terms of velocity and acceleration? So if you are in a car accelerating, you're putting your foot on the gas, you're accelerating along, and you're moving forward, okay, then your velocity is positive because you're moving forward, and your acceleration is positive because you're accelerating, okay? That means you're speeding up, okay? So you can be speeding up if your velocity and acceleration are both positive. You could also be speeding up if you're going backwards, so your velocity is negative, and you're speeding up in the negative direction. You're like pushing on the accelerator, but you're going backwards. In that case, your acceleration is also negative because you're accelerating in the opposite direction. So your velocity and your acceleration are both in the same direction. You're accelerating backwards. Okay, so you can be speeding up even if your acceleration is negative, as long as your velocity and acceleration are in the same direction. You're moving backwards and you're accelerating backwards. You'll be slowing down if you're like moving forward, but you're putting the brakes on. So your acceleration is in the opposite direction. So speeding up does not mean acceleration is positive. Do not think that. Speeding up means velocity and acceleration have the same sign. Slowing down means velocity and acceleration have opposite signs. Okay, so don't get this wrong. Speeding up and slowing down depend on both velocity and acceleration. We have to look at the two of them together. So what we're gonna do here is we're gonna do a sign chart for the acceleration as well, because we already have a sign chart for a velocity. So let me stick my sign chart for acceleration under this one. So let's do it down here. So this is my second derivative. Let's see, this guy will be, when will this be equal to 0? This will be equal to 0 at 3. So let's put our 3 there. I'm lining my 3 up here. If I plug in a number smaller than 3, like 1, I'm going to get a negative answer, and then I'm going to get positive if I plug in something bigger than 3. So let's look at these sign charts. I'm so sorry. And see where they have the same signs. So both are negative in this region. So the particle will be speeding up from 2 to 3, since acceleration and velocity are both negative. The ladybug is moving backwards, but accelerating. And then both have the same, they're both positive in this region. So from 4 to infinity, the ladybug's moving forward and speeding and accelerating. Okay. And then the ladybug will be slowing down everywhere else. So from 0 to 2 and from 3 to 4, because the signs of velocity and acceleration are opposite in those regions.